Przepraszam, kogo można by tu podbić delegację, żeby tak z pieczątką?
A, to w dziekanacie załatwimy jutro, jak pan jest.
Jutro, tak,
no bo,
tak,
bo
tak.
teraz to wie pan, 15:05, chyba że pan poleci do dziekanatu. Proszę bardzo.
Mogę spróbować.
Jeszcze pracujemy.
A dobry, no to dobře pracujeme v České republice. Ten Pavel byl říkal, že dostal 15 hodin, za 5 dní. Vlastně z toho si dopadl jako úplně většiny. A je to jedna samozřejmost. Ubytování chodilo. Takže mi říká ten Pavel. A tam nějakého pracujícího, on došel těho půlce ráno a mě teda spodíval se pana moc zabil. A oni spali jakoby na pokoji vždycky jeden, měl svůj pokoj a mě dělal tu kuchyňskou linku na druhé. A pak zjistil, že to není žádný pracující, ale to bohužel klikaluj. No, já to nás chtěla pláchovat, jsem se hrál. Ve 4 ráno, ale taky udělal zatáhnout, jo, jsem říkal. Pavel líčilo pracující, nebo Jo, to my jsme potřebovali 3 z každé skupiny, bylo 15, takhle zábilo víc, viděl té funkce. No, nepatří, jo. Takže to bylo jako dobré, že jsme dodrželi, co jsme potřebovali, ale víš, on na takové i to intenzivně na to přijeli větší. On zase moc dobře vidět, co chodí, že on taky to. No.
Nicméně bylo,
jo, to víš, dobré, že už
to wszystko, co się dało, zrobiłem za ramisem. Ostatecznie przez zginanie, przez skręcanie.
To ještě nevíš.
Wyboczenie zginanie. I zrobiłem im takie filmiki, nagrałem. Pokazywałem im po kolei krzyżowe rzeczy. Mamy się też patrzą na jeden wyczyn.
No, já jsem to už trošku dávno. To bylo trapně, ale vlastně co zmizel, no, na ten další jako, bude 5 hodin, 4, za toho vlastně nejde do půl, to se stalo hodně brzo, no.
take your seats. It is time to start this first afternoon session. And it's my honor and pleasure to chair this session. However, I must say that the main duty of the chairman is to control the time of presentation. Thus, I say to our lecturers, then 1 minute before your time is over, I will stand up to let you conclude your presentation. And the first lecture is a long one, general lecture, I guess. And we have our visitors from Brno Technological University or Technical University. And the authors are Stanisław Seitl, Paweł Pokorny, Wit Kriwy, Jan Klusak, and presenter is Professor Stanisław Seitl. Please.
Okay, thank you very much, Mr. Chairman, for that introduction. My contribution is entitled Experimental Investigation of Fatigue Behavior of Steel 460. And this steel is in a shape of plate with cruciform joints. This article is prepared together with Ostrava University. There is associate professor with CB, who is responsible for corrosion effect around this cruciform joints. Okay. I don't know which way I could aim when I. Next slide, please. This way. Now? Perfect. I think that it is quite good to say something about the motivation. Okay, I'm working at the Faculty of Civil Engineering. Therefore, for us, it is so important, so important structures which is loaded with variable loads. It is the first one is the bridges. Yeah, and of course, if the bridges, we can use the stresses. Perfect. From fluctuation of winds, but also with from vehicles or trains. It means that why we use high strength steel. It is because we reduce the size of the cross section and also degrees of the dead weight of the structure. This is so important for us. And then if we use both combination, it means that we need some fatigue measurement, and then we prepare according to this measurement some recommendation how to use this high strength steel. Okay, therefore, our aim it is to firstly introduce shortly material properties of the material properties, weaker toughness or weaker hardness, SNKRF, compare and discuss the results, and then later we add some corrosion effect. One more, please.
Should work.
Now, the chemical composition, it is quite easy. It is given by the producer of the steel, and it is some recommendation up to this value of the chemical composition, and there is any information about the real values of the chemical composition in this given steel plate. Then you can see here, only for information, how is the gray side. This is the 50 microns. It means that it is the standard steel structure. Okay, then we move to tensile property. It is according to the norm, we need at least the minimum value of the 460. It is the yield stress, ultimate stress. It is in this interval. Then you can see the measurement we perform on 5 coupons, and then there is the information about the average values. It is 490 and 625. It means that the steel, it is perfectly in the category of the steel
as 460. Then the other step, it was the measurement of the wicker hardness. Yeah, you can see there. And this information, it is for us because then important because we are going later to weld it this steel together. It means that there will be other areas which is not the pure steel 460, and then we try to measure the values around this welded part. You can see that the average of the wicker's hardness was 200, and of course it is not only surface information but also the perpendicular one, and it is in this direction. It was 184. We move it. And the other step, it is the information about the SN curves. All our measurement we perform in the stress ratio 0.1, which is so important stress ratio for the civil engineering structures. You can see that the information, it is very homogeneous. It is 0.8, the index of this dispersion, and here you can see the specimen which is unbroken in this level 220. It means that according to the stress ratio is 0.1, it is approximately 440 or 450. It is the limit for the cyclic load. Then we move to the specimens which we prepared from the study materials, which is welded. You can see that the weld was given in this, like in the cross section, and then we cut it. Primary cuts, we do it in 2 millimeters. It is for SN curve to obtain the information about the fatigue resistance, and 10 millimeters. It was milling and later polishing to obtain the net of the measurement for the wickers. Okay, we move it. Firstly, the easy measurement which was performed by wickers hardness results. You can see here the net and the map, how it's changed the value of the wickers hardness. It is from relatively from 0 up to 410. It means that where you can see these maps that the value of the wicker hardness were over the 410. Now the net, it is given here, and you can see these 3 corners from the measurement. I use the red color to catch the part of the specimen which was under the weld area. You can see A, B, C, D. That you obtain the information from average values in these areas and the all average value for all welded parts. Okay. Then we move for so important results, which is performed on this joints, and now you can see 3 results. The first one, it is well known from circular specimen. Then we prepare the measurement in the plate, and then the plate with weld joints. You can see that each geometry change the fatigue behavior of the material. Yeah. Especially when we see the endurance limits, which is 1 × 10⁷. You can see also that all points, if we are approaching the static test, that it is aiming to the 131 point. We of course before we prepare the test, we look in the literature if it's this effect. It is described. We found it that is already best described on the steel BS 4360, and you can see that the pure specimen, it is really shifted than the specimen with the cruciform joints. Okay, then as you saw it, the results, we have to these results quantified. It is the first is very easy. It was by Pascal model. It was not necessary to show it. Theoretically, it's so good to show it in log scale, but in my case, I use log information in the x-axis, and then the standard it means the semi-logarithmic axis for comparison of the results. Then you can see that it is also when we use the cruciform or the plate that the results, the index of dispersion is almost better than for the pure material. Yeah, because I suppose that it is initiated from the same defect, and also I suppose that the plate, it is quite understandable that the crack initiated in the surface where is the corn, where is the stress so in the high level than in the middle where is the old place in the normal. There is no any typical stress concentrator. Okay, then we look how is crack initiation happened, and we found it that all according as we suppose, and we know from the literature, it's come from the welt toe. You can see in the red rings like this. That this is always over the welt part. Okay, then the other step of our research was that we would like to control and what happened when we give it this steel in the corrosion. Then you can see that we already prepared the experimental campaign for 3, 6, and formally for 9 days, but it is 6 days in the chamber for 45 and 3 days in the chamber for 50 degrees of Celsius. And then the last set, the fourth set, it is from the roof extension sample, which is stay in this roof 1 year. Okay, you can see the chamber for the corrosion, and then how we tested these samples. These samples we use, you can see here, this 5, it is one, it is clear specimen, and then each one with the different corrosion effect. Then also for stress ratio 0.1, and then we started the test. When after this test, we also used the Baskin model for evaluation, or we extended one for Castillo-Cantoni model, because we would like to know it also not only the probability of the rupture of the specimen with 50%, but with 0.5 or 0.95, and if we are able to calculate with probability of the rupture with 0 level. Okay, you can see the first one. The Baskin model, it is quite clear. Applied, and then the problem, the problematic part of the Cantelli model, it is that it is described for hyperbolic. It's almost hyperbolic. This means that according to the rules that we start also for Baskin evaluated from 10,000 of the cycles. Also, we need to start for Castillo and Cantelli model. Okay, this is the reference one, and then the comparison of all 4 situations after the expansion in the chamber. Okay, you can see 3 days. Then, as we supposed, 6 days and 9 days. Then we added the corrosion effect after 1 year on the roof. You can see that this is between the clear and up to 3 days. Yeah, it means that if we wanted to simulate the situation in the Czech Republic, what happened with the high strength steel, the corrosion effect, it is clear that we could use 3 days as the 1 year approximately in the corrosion, or less than 3 days. Okay, there is some clear evaluation. You can see what is the probability of application of the description, and here you can see the amplitude value for 100,000 cycles and also for endurance limit. And then you can compare how we change the value. You can see that 70.5 or 70.4, it is almost the same, but then you see for 100,000 cycles it's 26, but when near the endurance limit is 32. Then for 9 days it is 30% down, but here is 50. And as we saw it before, for the roof, it is in this position, the green one. Also, you can see that there is only degrees 5% or 10% for endurance limit. Okay, then we look what happened on the surface. Yeah, because we suppose that the corrosion effect is on the surface, it means that the crack starts surely from the surface. As you see it, this is the reference one, theoretically without the crack prepared by corrosion. Then from exterior, because it's the second one which is follow the corrosion. Then for 3 days, 6 days, and for 9 days, you can see that every adding the corrosion change the surface much worse. Yeah, especially in the last figure. And you can see the points which is taken from this measurement. Then what is this for 200,000 cycles? Also, you see that here the crack propagate formally up to brittle rupture, and then you see that the corrosion is going inside during these more days. And the last two slides show us the reference one, exterior, and 6 days in this level, and then for all we try to finally evaluate. As I showed you before, it is the degrees is bearing capacity due to corrosion is clearly visible. It is from the results, it's quite clear. You can see that the degrees due to the corrosion, and then it is quite clear that the corrosion influence the fatigue properties. And if we would like to give together with some part of welded specimens, it means that we have to take together at least 2 effects, one for corrosion and one for weld. And it means that surely the properties will be I suppose the third one. But we just prepared the specimen. You can see one of them for the testing, but we didn't test yet. But I think that it is the last one which we are going to prepare during 1 month, and we will finish all our experimental campaign for this high strength steel S460, and we will be able to quantify not only effect of the weld, but also effect of the weld together with effect of the corrosion. Okay, thank you very much for attention. And
not faster than at all.
Yeah.
Program, yes. Okay. So this presentation under discussion now. Ask questions, comments, and so on. Yes.
Maybe I.
Mr.
Well,
Leszek?
nice lecture about the bridges. Knowing we have a lot of bridges, many of them were built at the turn of the 19th and 20th century. I'd like to ask you about some results, which we done also for all type of the material, completely not possible to compare with pure steel, but we tested some materials under fatigue loading after immersion in the corrosive environment, and also we tried to test in situ in the corrosive environment. Could you comment which method should be better or more realistic for capture the fatigue properties of material? Do you have maybe the comments or directions for people responsible for bridges?
It is a very difficult question, but thank you for for this. But I think that for quantification, because you never know how long the bridge is influenced by corrosion. But as you see it here, for example, that after we apply the corrosion effect from the roof, and then we try to 3, 6, and 9 days, that you can see that it will be, I suppose, especially in the endurance limit, we surely try to find some advanced description how to change the properties due to corrosion, and we try to use some function to be able to predict in the future how it's change the properties. Yeah, but if it's better to measure the properties in after 3 days, and we also know that when we take it out, we immediately start the measure, not to be like to have the exactly 3 days, because if we, for example, perform the test 1 month later, surely the corrosion effect or corrosion is continue inside. It will, so for example, if you do it inside or during this corrosion effect, I don't know what will be added value. If you, for example, wanted to look it when the crack will be better, if you have, for example, some crack that for example, some oxidative crack could be more quick or retard, or it.
Or generally speaking, in propagation.
Yeah, but there is not this effect case, because we suppose that if we use this only initiation is enough. And to
thank you.
Thank you. More questions or comments? Anyway, I'm sorry for introducing you coming from Brno, but you are from Ostrava.
No. It was no. It's from Ostrava was my colleague with Krivi. Okay. I only wanted to add it as a team member, yeah, but the rest we are from Brno.
Okay, fine.
Yeah, this was the purple. This purple man was from Ostrava. Thank because you. Ostrava is Faculty of Engineering is in this purple color. Yeah, it was. We try to keep it. Yeah.
Thank you. Anyway, now it's time for 2 presentations from Wrocław University of Technology, and I must say that the third paper from the list is cancelled out, so we have more time for discussion. I will not be so strict with time, so you can just present your papers as long as you wish. Okay, so the next paper is by Krajowa. We know you already, and Dariusz Peka, Mirosław Bocian, and Andrzej Kurzawa, and Krzysztof Jamrozik, and title will be certainly on the screen. So take your time.
Good afternoon once again. My name is And I'll be talking briefly on ballistic and structural performance of the SESJA with varying thicknesses subjected to unusual loads. Okay, and thank you, sir. I'm from this department, Mechanics, Structural and Biomedical Engineering. And these are the authors, Java, and Krajowa. This is an extract of the progress or parts of my PhD dissertation. So it's just an extra. Okay. So the content of this presentation is general review policy, subjects, and scope of research, description of analytic work, numeric analysis, results and conclusion, and I'll draw the kind of conclusion. Okay, so here is the general review of analytic detection. And what we're trying to do is we try to detect or to combat from the kind of threat. And when we talk about threat, the threat could include bullets, it could be shrapnels, it could be spark, it could be space for the battlefield. And what we try to do is to create multiple layers of material. We thought that this material is able in such a way that this material is able to resist or stop these threats and thereby not causing harm to our troop on the battlefield. And when we talk about multi-layer armor system, just from the name multi-layer, that is multiple layer, that is, we can have first, we can have second, we can have third. And most of the time, we try to fabricate the material in such a way that the weight is not too much to cause some fatigue on the person that is putting it on, because this is one of the things that we put into consideration whenever we are fabricating multi-layer armor system. The mass shouldn't be too much, or the weight, let's say, shouldn't be too much because of mobility. Imagine that you're putting on a armor vest that's made of steel. You cannot move from one point to another, you're already fatigued. So we try to fabricate material that is light enough and is able to absorb sufficient energy in such a way that the energy is not transferred to the human body, that's the person that is wearing it. And when we talk about multi-layer armor system, most of the time we are always considering a composite material, because composite material is actually a good material that is being used today, unlike donkey years ago, where we have metallic steel, which is not in vogue anymore, and now we use composite material. And most of the time, this composite material, we always try to checkmate the matrix system and also the reinforcing phase. And when we talk about the reinforcing phase, mostly we consider like fiber material like aramids or Kevlar, different kind of material that you could use to reinforce the matrix system. So in my own case, I am considering this PD material, like I showed from my title, this PD material as the matrix system, because from literature, so far so good till today, we can say there is just one article that has highlighted the use of this PD as a matrix material for ballistic protection. And it was published like a few weeks ago, actually. And the overall outlook is something like this. I mean, this is what we see if we watch action movies, you can see our soldiers, the way they put it on, it's always like this. So we try to protect them. And the schematic view of a ballistic test actually looks like this. This is actually like a test stand. So the material is positioned like 10 meters away from where you want to shoot the ammunition, or you want to shoot the bullet. And for my own research, I'm considering for today just this PD material, and that the bullets I'm considering is 7.62 by 39 millimeter. It's full metal jacketed like a NATO standard. And this bullet is made of 3 components. The first part is the core, then the filler, and the jacket. And in this case, the jacket is made of brass, the filler is made of lead, and the core is made of steel material. So which means if we have a core of steel material and we have a core that's made of lead, you can expect the damage that the one with steel core will cause compared with the one with lead material. So the damage from this one is so huge, and that's why I'm actually considering this one instead of lead, even though my PhD covers both of them. But for this presentation for today, it's strictly steel core. So this is a pictorial view of a dissipated plate is 5 millimeters. And for my research, I consider 50 by 50 millimeter samples that is made of DCPD, and I consider different thicknesses like 5, 10, and 8 millimeters. And after quasi-static tests, I was able to come up with this constitutive model. I mean, the material properties of this DCPD from the Young modulus to the fracture strain, and this actually is detailed from the table. And from the test, here is the pictorial view of the test in the laboratory, and here is the 3-point bending test result that we have the force to the displacement. And for the stress strain information, we have it here, and the fracture strain is about 0.035. And this fracture strain is kind of crucial for me. I mean, it's a very important information because I would need it for the numerical calculation, especially when I want to see how this material actually fractured and turned into maybe some particles. Like the first lecture we had in the morning that was talking about smoothed particles, hydrodynamics. It was also considered here. And before we move forward, I would talk briefly about this SEM analysis of this bullet. So you can see here that from this portion that was chosen here, which is the steel core, it looks like this. This is just a slice of the bullet. So when you slice it, you are able to see the core, you're able to see the filler, and you're able to see the jacket. So here is the core. The next layer that you are seeing here is the lead filler, and what you see here is the jacket. And you can see from here, from the percentage of the weight of each chemical composition, you can tell that this is, you can see the proportion of iron here is about 94%. So definitely this is a steel core, right? And from the next slide here, you can see for the lead filler, which is the second layer that follows the core, depending on the direction you are viewing. If you view from the above, it means next to the jacket. And if you view from inside, that is, you can say it's next to the core. So we have the lead filler here, and you can tell from the proportion or the amount here, which is about 93.8%. And for the numerical calculation, because I'm considering metallic material, and this is one of the models that is often used in literature, and it has proven over time to be really valid and effective, which is Johnson-Cook model. We have this flow stress, which is equal to these parameters. However, for my own case, I did not consider the effects of temperature. It was kind of not included here. And the plates were fixed in all directions in such a way that there's no degree of freedom. There's no movements. In other words, there's no movements in all axes. That is, it's fixed because this is how it should look like in real life when you mount your sample before you fire the ammunition to it. And I consider impact velocity of 710 meters per second. However, the velocity of this bullet naturally is between 710 and 730. So in my own case, for my calculation, I use 710 meters per second, which is quite sufficient. But recall that because there's a direct relationship between kinetic energy and the velocity, right? Which means if I reduce my velocity from 730 to 710, it will have an influence on the kinetic energy, right? Because there's a direct relationship between them. I'm going to show you how it actually affects that. So description of the bullets used for the simulation. So because we have to check the constitutive model for the bullet itself. So this is the steel core. It has these parameters, A, B, M, and N, because these informations, we need them to do our numerical calculations. So for the lead filler, we have this, and for the brass jackets, we have this information. So this is just the pictorial view of what it looks like. The outside layer with the jacket, the filler, and the core. This is just a discretization of the whole bullet. Now for the resulting discussion, we can see a complete penetration. That is, this sample, this 5 millimeter thickness of dissipated plate is unable to stop this bullet. There was a complete penetration in which you can see like there's some the material fractured here. You can see the particles. We set this before we can actually have this information. We set it in such a way that the stress strain information that we have, because we have the fracture strain, so we use the condition of the fracture strain so that whenever it actually gets to that point, we have this kind of information. And this is what it looks like in real life when you shoot it. So there's a full penetration with these bullets, consider this thickness. So this is the side view, and this is the front view, and we have the von Mises stress information here from this slide. And for the second sample, which is 8 millimeter DCPD, the same thing happened. However, there is a difference in the size of the damage or the size of the penetration. The only difference that we observe in here is the size of the penetration. Of course, there is a complete penetration here, which does not mean this result is bad. This is what we actually expected, because no one expects a DCPD material to resist that kind of bullet with that impact velocity. So this is the size of it. And from the side view, you can see that there's a complete penetration. However, there's something I would like to point attention to here. The tip of the bullet here is always flattened, but we're not going to go into details today because this might be a subject for another day. So it's always flattened. And why? It's actually due to the fact that whenever you shoot this bullet will absorb some impact energy. This plate will also absorb some more, and the rest will be transferred back to the bullet itself. That's why you have a flattened tip of the bullet. And for the last plate of 10 millimeter DCPD plate, the same thing happened. There was a complete penetration. As you can see, the tip of the bullet showing here. And whenever you see this this effect, you can see that the plate is unable to resist or to stop this bullet. Even though the plate was able to absorb some impact energy, the load was transferred back to the bullet itself, which led to the flattened tip of the bullet here. So in other words, what I'm trying to say is the size of the damage of the bullet, even though there was a complete penetration, differs based on thicknesses. Now, here, to validate the numerical calculation, we compare with the experimental result. And for the size here, we have about 20 millimeters. And for the same thickness, for the same plates, we have 39.6. So it's just a little bit small difference, right? And for this second one, we have 11.7. And for the numerical calculation, we have 11.13, just a bit insignificant. So for the bullet itself, because it will be important to also show how the velocity of this bullet drops with time. So the flat region here is when the bullet is in the air and has not touched the sample yet. So by the time it touched the sample, you can see how the velocity drops until here. You can see that, in the relationship between velocity and time is when the velocity actually gets to zero, it means the bullet stops. That's the implication. But you can see that it's not up to zero here. It's just from 710 up to somewhere around 706. So it means the bullet was still going. But we don't need that information. The information we need is there was a complete penetration. And that's why this velocity drop does not get up to zero level. And for the kinetic energy of the bullets, it has to look similar, or in a way such that it gives us information about the velocity, like you said before, that there's a direct relationship between the kinetic energy of the bullet and the velocity itself. So the kinetic energy also drops. It starts dropping from the point at which we have the contact of the bullet and the sample. And it doesn't get to, you can see that it's not even up to zero, because you start from 1990, a bit more. And the energy of this kind of bullet is about 2,100 joules. But because I use 710 meters per second velocity, I have this. But if I use the real impact velocity of this bullet, which is about 730, then by calculation, I should have 2,100 joules. So the energy drops until it gets to this place. So the implication is, even though this material was not able to resist or stop this bullet, it was able to absorb at least little of it, and some part was even transferred back to the bullet. So this is what we can see here on this plot. And the next thing to do for me, after this whole thing, is to now construct the composite material using the DCPD as the matrix system and use the aramid fiber that I plan to use as a reinforcing face. Then I will consider different thicknesses, different proportion of the matrix, different proportion of the reinforcing phase, then check the ballistic impact on this material and compare with numerical calculation. And this will be the next thing to do based on the outcome of this result. And now the conclusion. A numerical investigation was conducted to examine the ballistic impact effects on solid dissipate plates with varying thicknesses. This is exactly what I just discussed. And the finding of this simulation showed that a complete penetration occurred with different depths and circumference of penetration, like I showed in the 2 slides before. And a little plastic deformation occurred at the tip of the bullets as a result of the impacts. So this is the whole conclusion I came up with from this presentation. Thank you for your attention.
Thank you. Very nice paper. It must be a very nice PhD thesis also.
Thank you.
And now it's time for discussion. Paper is open for discussion. Oh, please.
Just a short one. Slide number 5. You have the Young modulus is 0.1 gigapascal. Is this the Young modulus for the polymer?
I think that's some, it should be megapascal. Gigapascal?
It says 2.1.
2.1 of the polymer, this is PD?
The Young modulus.
Yes.
This is the Young modulus for this.
This is PD material? Yes.
Just pressed with a very low Young modulus.
Yeah, it is low. Yeah. Yeah.
Right. That was it.
Yeah, thank you.
Another question, please.
Actually, I would be interested in what will be the benefit of using DCPD instead of, for instance, epoxy. That would be the first question. And the second one, did you apply any failure criteria for FEA?
Okay, thank you for your question. So I will start from the first one you asked, that's why do we consider this? Okay, like I mentioned from the introduction, this PD has never been used. So technically, we might be the first person to put it on internet, yeah? And because this is the essence of research, we have to keep finding new things, yeah? That's one point. Another point I would say is from the published work that we published a few weeks ago, we actually used this PD, and it shows that these results shows some very good outcome when it comes to ballistic material, especially when it comes to matrix system, far beyond like epoxy resin and stuff like that. Like it was really, really better results. If you don't mind, I can show you this paper and you can go through it and you'll definitely appreciate it. And for the failure criterion that you mentioned, because of the constitutive model that I used here, from the stress strain curve here, I could see that the material actually failed at this strain level. So I use fracture strain as the failure criterion for the DCPD. Of course, I could use stress, but it is really better to use strain because it is easier. And based on the software, Abacus, you can easily impute this kind of value, then the material behaves exactly the way it should be when compared to real life situation. Thank you.
Next question.
Yeah, sorry, I didn't get the question. The bullet? Okay. Yeah, the bullet we consider, or that I consider, is 7.62 by 39 millimeters NATO standard. That has a impact velocity of 730, between 710 to 730, with energy of 2,100 joules. Yeah.
But you show the failure strain for statics.
For static, yes.
But you have dynamic situation.
Yeah, you know, dynamics is really a complex thing. And sometimes you have to justify the results by considering what we have from quasi-statics tests. Because like if we can get the constitutive models from the static results, we can think how this material would behave in a static way, even though they are not really.
But certainly the strain would be lower.
When it comes to dynamics.
How much, I don't know.
Maybe it's something I would like to check in the future.
Okay, thank you. Thank you very much. More questions? One more, please, Mr. Seidel.
Okay. Okay, Professor. This one? Good. Yeah. Less than one?
Yeah. You measure or how you explain the barcode?
Okay. Okay, thank you for your question. Okay, the way I actually estimated this 1.2 share modulus is I try to use the equation that relates Young modulus and Poisson ratio, and I was able to get this. If this is wrong, based on what you suggested or what you said, then it might be some kind of calculation error that I will have to revisit and check again. Yeah.
Thank you. No more questions? Thank you very much.
Thank you so much.
Next presentation is again from the Wrocław, and several co-authors, Dr. Bem, Kluger, Osiecki, Schubert, and Banasciuti.
It's from Opole University.
Opole, thank you. Thank you. All of them? Oh, yeah, I'm sorry.
No, we have a cooperation with 3 universities
And
on this paper. Yeah, exactly. Tak, tak, musi być. A można wyłączyć naznaczenia. Okay. Okay. Dear Chairman, ladies and gentlemen, thank you very much for the opportunity to present one of my papers. So this paper was created in cooperation with the Technical University at Chemnitz and the University degli Studi di Ferrara from Italy. So we are working on many topics. One of these topics is exactly as you can see, fatigue behavior of 3D printed titanium, aluminum, vanadium specimens with ferric stress concentrator void. So the specimens have been printed with the use of metallic powder. And this is my agenda. So introduction, material, specimens, static test results, fatigue test results, conclusions, and observations. This will be a little bit broader, wider than I just presented as here, but everything will be explained. Okay, so in order to for a powder to be used for high quality metal printing, the physical properties of this powder it has to be spherical, smooth, equally sized, very fine, and have a low oxygen content, right? So this is perfect for us if you want to create it, sell it. We don't want the powder to be trapped inside the element while printing complicated shapes during the process. That is why we need to remove it before closing gaps or voids, as you can see on this picture. So the powder removal is actually one of additive manufacturing dirty secrets, right? We have many techniques. We don't want to have the powder anywhere. We have vacuum boiling. We have some ultrasonic techniques, which we can apply in order to remove the powder from complicated shapes, space, and so on, right? So one of our meetings, because we are printing a lot of things together, we actually discussed, it doesn't do anything. Okay. What will happen if we don't remove the powder during the printing process and leave it in the voids, right? I'm not talking about the pores, I'm talking about voids, right? So the spaces that have been created according to some complicated structures and so on. So there have been some papers on fatigue in terms of powder contamination of the structure of the samples, of the influence of different pores, right? But what happens if we just leave this inside the void? So How would this influence the fatigue properties of a printed element? It will speed up the printing process because we don't have to stop the process. We don't have to blow out the powder, right? And increase the weight of the construction, but it will have other effects as well, right? So in order to try to answer these questions, the authors have performed experimental fatigue tests of 3D printed specimens. And the goal of this paper is to test fatigue specimens with powder trapped inside a void, pre-designed void, in the shape of a sphere under constant amplitude bending, right? So we designed a 3D model, we designed a sphere, but if it's going to be a sphere or not, we will see after the printing process, right? Because the printer also has its capabilities. So the material that we have chosen for this is titanium, right? Aluminium, vanadium, grade 5. It is comprised of 90% titanium, 6% aluminium, and 4% vanadium. The positive aspects of this material is its high corrosion resistance, high tensile strength and light weight, low density, heat treatable, easy weldability, and fabricability, excellent biocompatibility. It's non-magnetic. It has some disadvantages as well as poor shear strength and corrosive to strong acids. The mechanical properties, we can see high ultimate strength, tensile strength, yield, right, elongational break, and the modulus of plasticity is not bad for a material like this. The samples that we have, so specimens that we have used, so these are actually, as you can see, the upper one on the left is the full fatigue specimen that we normally use for fatigue tests at the Poland University of Technology. It is called the Diabolo specimen. On the right side, we have tensile specimen that was being used by, which our partners wanted to use during the test. And on the lower side, on the lower left corner, we have the fatigue specimen with the spheric void. So we actually have two types of fatigue specimens in doing those tests. We are testing the full fatigue specimens printed, so full, no voids inside. And we have the fatigue specimens with the spheric void inside that is filled up with the powder. So we are not stopping the process. We are not blowing out the powder. We are just leaving it there. We want to see how it will influence the fatigue properties. And the fatigue properties, in my aspect, we want to check it up to the moment where we have the initiation of the crack. So we are not discussing the propagation of the crack in this paper. So as for the buildup, we had two sets of fatigue specimens. We had one set of tensile specimens. In the first, all of these tests have been built. The specimens have been built in the direction of the z-axis, as you can see on the right side. The diameter was 3 for the special sample specimens. This is how we got the specimens from our partner from Chemnitz. The specimens have been also heat treated 675 degrees Celsius for 6 hours under argon atmosphere. And then we have also machined them, right? Because we want to highlight the aspect, if there is an aspect to be found when it comes to the void, right? We want to, normally we could test the samples as they have been printed, but usually there are too many disadvantages in terms of the roughness of the surface. So maybe it wouldn't show a clear result in these terms. So we have machined the specimens, and we have machined also the specimens for the tensile tests. It's good to, it happened that we have the company Lenso. So in a few days, there are going to be ZEISS. We have used their software during the test because we also have performed tomography of all of our samples. We have used GOM Inspect Pro for that purpose. So it's interesting that we met up here. So we could assume, we could calculate the whole area, all the pores that have been inside the specimens. We have all the data that can be later analyzed. We can create the 3D models for the finite element method and so on, right? So we have all the data. So the perfect situation would be like this. If we have the scan of our void like this, nothing beside it, but in some of our specimens, we have something like an artifact presumably something that has been maybe a computer failure or something during the printing process has also occurred. Because we have also measured that area. As you can see, it's enlarged on the right side, right? We have measured it's something like a ring element, a little bit coney, so like a cone being cut. In some specimens, we have this area that maybe later on can influence the fatigue tests, as we can assume. So as for the fatigue tests, we have obtained the ultimate strength at the 1,164 megapascals. The yield strength is 704. The Young modulus 110. As for the fatigue tests, we have used one of our constant amplitude bending test stands, the test stand MZGS 100 for bending and torsional tests. So it allows us constant amplitude testing under higher frequencies up to almost 30 hertz. So as for the first results, so for the full specimens, right, the specimens without any void, that should be the reference specimens for our reference fatigue curve that we are going to have for bending of these specimens. These are the results for 18 specimens, the Diabolo fatigue specimens, still the crack initiation. So we didn't discuss the propagation. The cracks occurred exactly in the center, most of the time in the center of the specimen. So where we have designed the area where the crack normally should appear. Beside this, we have also the fatigue curve for the specimens with the void inside. And as you can notice on this picture, the crack didn't occur in the center, but as you can see by the red lines, it has occurred a little bit to the side of the void, right? And it appeared every time around this area. It never appeared in the center where we presumed would be the weakest area, right? Because there is this void, it's filled with powder, but it's still the void. This should be the weakest area. If we put them together on one diagram, you can see they look like this. The levels in terms of the tests have been chosen to be the same. So after we had the scans, we have measured the diameters of the voids for every specimens, and we have calculated what should be the bending moment in order to obtain the same stress levels as for the full specimens. So as you can see, we have obtained results like this. So we can notice that it doesn't influence that the powder, it doesn't change it doesn't improve the fatigue capabilities in terms of a normal full printed specimens, as it was also expected. And beside this, we have made a lot of tests in terms of scanning surface, 3D surface roughness, 2D surface roughness, and so on. One of the elements I would like to show you is the fatigue test results for the 3D roughness depth of the initiation crack, right? So it's in Polish because at first I didn't know if I should prepare everything in English. Some of the diagrams they had also elements in Polish because Polish software, but the maximal depth for this for the crack that we had was 34 micrometers for this analyzed specimen. Beside this, we have also performed a cross section of the whole sample, right? First of all, we cut it through. You were expecting maybe there's nothing there. Maybe our partners, they didn't left the powder inside, but as the scans proved, it was also there. It went outside after we cut it through. And this is the surface that you can see with the use of specialized software for the software. The machine is called SensoFar, and this is used in order to calculate the height, the roughness of surfaces, to measure areas, and so on. As you can see in this specimen, there was also no, maybe you cannot see, but I didn't highlight it. but in the area where we had those artifacts, we don't see any effect on this. So there is no additional element where during a CT scan we would have this area that was there was on the image. So maybe while we were cutting this, it was melted or something else happened, but we cannot see it after the cross-section cut. We also performed a cross-section sphere roughness examination. As you can see, it was roughly 17.5 micrometers, right? We also analyzed the surface. We always want to have smooth specimens, but during the printing process, we had to agree to have a higher roughness on the surface of the specimen even after the machining, because it just didn't apply to lower values as we wanted to. These are equipment, our specialists that performed that didn't have the skills to do it for this material because some other topics. Okay. As for the conclusions observations, so the specimens with the spherical void had many inclusions, and some of them had something we can call printing artifacts. These specimens didn't have the initiation of the crack in the center of part of the specimens, but in the area of 5 to 50 meters of the edge of the sphere, and always outside the area. The specimens with the spherical void have a lower fatigue life in comparison to the full specimens as expected. Additional fatigue tests should be performed, especially under torsional loading as well as variable amplitude loading and in other printing direction, right? Because we printed them in the direction of the z-axis. Maybe we should also apply 45 degrees in both axes, maybe in the x or y direction. Maybe these tests will look differently. The results will be helpful in planning of the printing strategy and the author's plan to perform fatigue tests for different void shapes and prepare a catalog of void shape influence for the trapped powder. So this is our goal. We are planning to prepare a grant application for this, because I'm only showing experimental research here, but we are also working on the finite element method calculation for these cases. And as you can imagine, while preparing the powder, how the powder is trapped inside, and the effects, we have a little more information on how it was, because as you can see in the here, for example, right, we can see there's something like the leftover, right, on the left side on this sphere, right, on this circle. Maybe this was a leftover, something they call a lattice during the printing process, right? Maybe it also appeared during the heat treatment process. Also possible, but shouldn't really happen for this material due to the temperature. Okay, do I have some additional time or not yet? Because
2-3 minutes.
2 minutes, okay, because I had some other pictures. So beside this, our partners also gave us information about, as they have printed it in Chemnitz, they also performed the microscopic pictures of the whole build. So for the full samples, you can see that really we had like the no pores for the specimens, like almost perfect, right? In the second case, I have chosen some pictures. There were more pores in regards of the whole printing process, right? So maybe this could also influence the fact that we didn't have the cracks exactly in the middle, but shouldn't be the case for all specimens, right? Because this happened for all specimens. Okay, so thank you for your attention. I hope we can cooperate. If you have any questions, I will.
Thank you very much. Yes, some questions, discussion, comments, please. Yes.
Thank you for this nice of the surface or inside of the shape?
On the surface.
So, and you have the specimen here and dark points which are included inside of the specimen.
Yeah.
To make that bending.
Yeah, exactly. So the bending is on the surface.
Yeah.
We have
I don't understand why this voice of the influence is which is the technician.
Yeah, I don't say it influenced. I don't have the answer why it's not in the center. It's away from the center. So this is just something I said. One of the scenarios, life scenarios, which could happen, right? Because we don't still have all the information.
I think it's not vacuum test, but outside.
Yeah.
Maybe this should be better.
Yeah. It's always easier to perform actual tests because we know everything about the stress, right? But in terms of this material, we have a lot of information about actual tests, different cases, not the void case, of course, not the void case, but if I should just perform actual tests for this material, and this is not, as you, I presume you know, this is not cheap material. This is not a cheap material usually. And if I want to, if you wanted to make something new, we have noted that there are not many bending results for fatigue tests for this material also. So while performing the basic curve also for the bending case, we have some additional information we can also give to the industry while we cooperate, right?
Thank you. More questions? No. Thank you very much.
Thank
you. The next paper is from Serbia, I think. Mr. Grabovic, Solop, and Alexander Sedmak. Who is presenter?
Yes, hello, I'm here. I'm ready.
Oh, yeah. It's not written here that this is.
Yes, I'm the
Hello,
oldest.
Alexander.
So, hello, Andrzej. How are you?
Nice. How are you?
It's a long time, about
Yes,
43 years. Okay, it's really a great pleasure. Well, I'm sorry that I'm not there at the spot, because not only that this is one very important event, and my greetings to organizers and to Polish group on fracture to be so active, but also Wrocław is one of the most beautiful cities in Europe. 12 rivers, 100 bridges, fantastic. So I will come, I promise, in 2025 for another conference, but this time I was really already signed in for something else. So at least we can see each other on the screen. And just a few other words before I start. Alexander Grbovic, who is the first author, is actually our main driving force in Belgrade, University of Belgrade, for this these analysis of fatigue crack growth, numerical analysis of fatigue crack growth by extended finite element method. He started working on it almost 10 years ago, and now there is activity so strong that I even call it from time to time the Belgrade School of Numerical Simulation of Fatigue Crack Growth. So both of my presentations, because I have two consecutive ones, will be on application of XFEM to certain problems. So let me start with the first one. I should share a screen now, I guess. And I hope you can see it. Is that correct? You can see and you can hear me. Is that right? Okay,
yes,
good.
It's okay.
Good. These online presentations are sometimes a bit worrying when you don't get any reply, and then after 10 minutes you realize that nobody is listening. I had another one today, and that was the case, and we had difficult time to stop the speaker. Anyhow, here we have, I'll put this to the, well, okay, it works. And let me remove also this if I can, but I can't. Okay, something like this. I hope this is better. Yes, so we are talking today about fatigue life in a way, in a crucial component of an aircraft, a small one. You can see here the sketch. Actually, it is a pin lug wing attachment. This is one of the most stressed part in all aircrafts, and in these small ones we can use some simple engineering equations which are based on these four schemes that you can see on the slide to get some analytical calculations. We did also some experimental analysis, and these two will not be presented today, but rather we will talk about XFEM simulation of fatigue crack growth. That was, by the way, most important parts of the thesis of the second author. He was our student from Libya. So now I would like to switch to the next slide, but this doesn't work. Okay, it does. Here we have some details which we should take into account and explain a bit. Those are the connection points in the fitting of this main spar, which actually holds the wing. It is a kind of a beam, relatively simple actually from mechanical engineering point of view, from stress analysis, relatively simple parts, but still what is critical here is this lug, which is under tension and also under transverse load, so some shear as well. And there are many cases of failure, or at least cracking. Well, cracking is typical, not exactly failure, because there are ways to prevent it, but still it could be also a failure from time to time. You can see here where cracks would typically occur, and this is actually the topic of our, this was the topic of our analysis. We started with a static analysis, and we were focused on lug, on this part, so you can see also basic dimensions here. You can notice this outer radius and these inner radii. They are important for the analysis that will follow. Thickness is 12. It's important because we will vary thickness in the last part of this presentation to get the optimal value, as well as these radii that I already mentioned. So static finite element analysis indicated, as you can see here, and in more details here, indicated the most stressed region. So our finite element model for the fatigue crack growth analysis was based on the static analysis. Sorry, that was wrong move. On the static analysis, so you can see here some kind of sketch for this model, and you can see where we put the initial crack. It is exactly the location where the static stress was the highest. Of course, that is a standard engineering analysis. And now you can see two of our first numerical simulation. When I say two, I mean two different meshes. We have used so-called hexahedral finite elements. This is abacus, by the way, I forgot to emphasize. And we are typically using two commercial softwares, Abacus and ANSYS. I will show later on comparison between them as well. But now we are looking just at the Abacus meshes, one with hexagonal elements and the other hexahedral, elements, and the other with tetrahedral mesh. In the first case, mesh is relatively uniform, as you can see. In the second case, you may notice that mesh was refined in the area of crack. So this is the presentation of corner crack. We have analyzed in this in the scope of this thesis two types of cracks. One was corner, the other one was going through the whole thickness, and later on we will focus to the later one. A few results just to show you about the stress intensity factor. It is three-dimensional analysis, of course, but still mode 1 is dominant, as you can also see from these results, because of you can see that mode 1 K1 is similar in value with K equivalent. You can also compare. I'm sorry, it's not completely visible. I don't know how to remove this. It goes from time to time on its own. So now you can see the complete slide. You can see that stress intensity factors are in relatively good agreement. In any case, tetrahedral mesh produced higher values of stress intensity factors, and therefore tetrahedral elements produced shorter lives. So you can see here in this slide, crack depth is dependent on number of cycles, and you can see relatively good agreement between these two meshes. And of course, you can see that tetrahedral elements produced more conservative result. I will not go into much detail and discussion about which one is better. At this point, we don't have time for that. And to be honest, we don't have a decisive conclusion on that, because unfortunately, we don't have experiment to verify this numerical simulation. So I will just state from time to time which one produces more conservative results, but at this point we still don't know which of these would be, let's say, better. We plan to do some more experiments in future. We did already some of them, but not verifying these results, but static results. Now, as I told you, corner crack was option 1. There was also through crack. You can see it on this slide, and you can see that we chose hexahedral elements to go on with them. So here is just a mesh for the step number 1, and on the right hand side it is the mesh for the last step, number 9. You can see that crack is now already all the way through. Numerical results are shown also in this table as indicating stress intensity factors, and then von Mises stresses are shown in the figure below. Now, improved FEM analysis is presented here just to show you some differences between numerical simulation by XFEM done in Abacus that I showed so far, and numerical analysis of fatigue crack growth done by ANSYS, but by the classical finite element method. That means using some special technique to reconstruct mesh in every crack step, but of course not by us. So that's what ANSYS is doing it on its own. That technique is called SMART technique, but that's acronym, not adjective. So here you can see how stresses are distributed in the first step, in the last step, and then you can see comparison between stress intensity factors for the finite element method and extended finite element method. And once again, I'm not commenting on which is better. Just we see from here that XFEM FEM produces more conservative results. Don't be confused. This was wrongly put here. This is why I put in red, but I couldn't delete it. So XFEM is orange and FEM is blue. So XFEM is more conservative. Sorry, I mixed it up at the end. Doesn't really matter at this point. We are still working on it, how to get the final verdict, which one is better. They are producing good results anyhow. That's the main point. And also, in this case, it was not so important because our goal was optimization of this attachment lag. So we played a lot with these numerical models, with this numerical simulation to find out which shape would be, and thickness as well, would be better and would produce more longer fatigue lives. That is something you can't do analytically. That is something that you can do experimentally, but the cost would be more than airplane itself. So we are left with numerical analysis to play like this. There were a couple of models used for this. This one is the original model, so it is 515. That's number of cycles for crack to grow from 0.5 millimeter to the critical value. This is almost the whole cross section. Then we made another model when we varied, increased, better to say, thickness. And of course, by increasing thickness, we would add some mass, but we would reduce, as you can see here, stress intensity factors. And so, in very natural way, we would get a larger number of cycles. Sorry, I have to go back. Here it is, almost double, 1085 compared to 515, actually more than double. That's really simple, but more complicated was what follows, model number 2. At the same time, we varied thickness and inner radius. So by doing so, we have 2 parameter optimization. And after analyzing of these results, we came up with yet another number of cycles, in this case 1933. So almost, once again, almost doubled compared to the previous option, and almost 4 times compared with the initial one. And then another two models now with 3-parameter optimization, not only thickness and one inner radius, but also outer radius. So just to show you a couple of results and to show you that the optimal combination in this case would produce a number of cycles which is in between previously stated values, so something around 1000. And the last one, something like that as well, 824. So to make a comparison of all of them, you can see here that far the best from point of view of number of cycles is that 2-parameter optimization, which was close to 2000. Now here it is a bit less because crack length is limited to 7 millimeters. And you may notice that original lug, of course, has the shortest life, and then others are in between. This table shows about the same. You can see here, even in percentage, what is the increase of number of cycles, but you can also see that at the same time, mass increase is the highest, where the number of cycles is the best. Therefore, to conclude, you saw what numerical simulation can do, and we can conclude that model 2 is the best from the point of view of number of cycles, but not from the point of view of mass. So if number of cycles is the only criterion, then we choose model number 2. If not, then we might choose maybe model number 4. And in any case, this is a bit of a play, so we still need to experimentally verify this, and then we can really apply it in real life. Thank you. That was about
Thank
the
you,
first
Alexander. Very
presentation.
nice paper. And let me open your paper for discussion
Okay.
and some questions or comments. Okay, Professor Leszuk.
Yeah. First of all, let me say great gratitude to Professor Sedmak as a president of SESJA that he found the time for us with the lecture. But I'd like to go quickly to the question. I see also a lot of effort, especially using numerical methods by calculation of the lag structures. I also had some experience, but maybe not so deeply like Professor, but I remember the problem of the modeling of the load. I mean, what kind of load distribution in your case was modeled? It was a kind of pressure, uniform, or maybe in different way, like cosine, non-uniform. I also remember that it strongly influenced the results of the stress intensity factors, and naturally, at final stage, it influenced also fatigue lifetime. Please share with us your experience in this matter.
I have to admit that my own experience in this matter is limited to trust my co-worker and friend Alexander Grbovic, who always simulate loading in different way to find out which way is the best one. So he would be capable of answering concretely this question, how he modeled loading, but I'm afraid I just would have to direct this question to him. And I believe we will write a paper on this, and in the paper, if it will be accepted, you will have all details, and of course we can continue this discussion through, let's say, emails, and I will certainly find out with Grbovic how he did it. Thank you for your question. It's a very important one.
Thank you.
Thank you.
Some more questions. I must say that the next presentation is again on numerical simulations, but now concerning the hip implants. And the
Yes,
author
indeed.
is Alexander, his son, I think Simon is your son, and Tamara Smoljanic.
Exactly.
Present Alexander the paper.
Yes, I'm the oldest, so I'm presenting
Okay,
it. Yes,
thank you.
yes. Thank you. So here we go. And this slideshow mode. Couple of more authors are listed here, but basically this simulation was done by Simon. By the way, he is right now in Dubrovnik for international conference on durability and integrity of structures, and also presenting papers like these two. And he is one of our one member of our team, working very closely with Grbovic. So let me get rid of this if possible. No, I can't do. No. I hope it will vanish on its own. So here we are dealing with hip implants. In this case, we have used titanium alloy, and our main goal was to analyze the effect of very harsh environment for hip implants, because human body is very unpleasant environment for metals. So we did it experimentally and numerically once again, and we were focused on two effects. One was moisture, humid environment, and the other was salty environment. So some in both cases we used for the experiments special chambers. We as you will see tested our specimens there to get mechanical properties, including coefficients for Paris law, and then we use them for numerical simulation. So we can call these three different conditions as normal, humid, and salty. And I still can't get rid of this bar. Oh, okay, this is slightly better. Yeah, now it's good. So as for the instruction, I think I mentioned most of important facts. Let me just say that, and you will see it soon, that we did have a problem with the fracture toughness testing, because we had only 2.2 millimeters of thickness of plates. So we couldn't get K1C, but anyhow, the basic idea here was to compare. And from previous experience, we also knew what value K1C would really have. So we decided to go on with KQ as a relative measure for these three states, and to use it to calculate, to evaluate critical crack length. That would not be in the plane strain condition, but still it would be in a kind of real condition, more or less. Then again, the other differences for these three states would be in Paris coefficients, as mentioned here. So C and M were also evaluated by testing in three different chambers. This is already said. Just to additionally inform you that these chambers were used for 30 days to get humid or salty conditions. And then testing, of course, was not done in chambers, but in a normal in a laboratory. So here you can see these specimens. CT specimens were used for KQ and of course for Paris law coefficients. And at the same time, we also tested tensor specimens to see the effect of human body on tensor properties. Here at the bottom, there is text explaining what I just told you about KQ versus K1C. So we covered that. Now you can see the results for stress strain diagrams, and you can see that about 10% of, or less than 10, 7-8% of reduction of yield strength is typical for salty condition and almost the same for humid condition. But salty condition, as you will see, is also the worst case for fracture mechanics parameters. Here you have a list of these 3x3 experiments. We had 3 specimens for each condition. And in red, I marked 2 specimens that were a bit surprised, especially for normal conditions. One will expect more uniform results, but you can see that yield strength was not exactly uniform. Tensor strength was. Nothing special about it, just to pay attention to that. And then again, for humid condition, of course, you might expect some discrepancies of results. But in any case, it's clear that normal condition has the best tensor properties, and humid conditions is somewhat better than salty condition. Not a big difference, though, one should notice even at this stage. Now, for the fracture toughness, these are 3 diagrams that we typically obtained, once again, for 3x3 experiments. This one is for normal condition, humid and salty conditions. And here are the results. So KQ, once again, in all 3 benches, all 3 conditions, we had one specimen which was a bit different than other 2. But we counted on average scale this effect of salty or humid conditions, and found out once again that normal is the best, then comes humid, and then comes salty. In the next step, we will try to make a chamber in which we can have salty and humid condition at the same time, but that's for the future work. Here is one of typical results of experiment for Paris law. It was done according to the standard procedure, and as the result, we got these pairs of C and M for normal, humid, and salty condition, and once again in the same order of the effect. So humid is less damaging than salty. And you will see this also by calculation. First, we made analytical calculation, just a simple analysis by using directly integrating Paris law, just to have the idea what we should expect. And these results are, of course, very conservative. So we were not surprised once we applied this XFEM, and you can see here the mesh, the boundary conditions, and the loading. You can see here on the right how the loading in this case was defined. You can see here also how this numerical model looks like after the last step of crack growth. Of course, crack was positioned at the most critical location. This is well known for everybody who is dealing with hip implants. And here are the results, just 3 different curves for crack length versus number of cycles. We go quickly through that. The second one and the third one for the humid conditions. So once we saw these results, we can conclude that 4,869,000 is the best fatigue behavior for normal conditions, of course. Then for humid condition, it reduces about 10 or less than 10% to 4,450,000, and the lowest is for salty conditions, 4,135,000 cycles. So that this is much larger prediction number in prediction than analytical one, but analytical one was really very conservative. So we think both of them are realistic in terms of how they were obtained. Once again, we will try to experimentally verify this numerical simulation. It is not simple, but not as complicated as it would be with the previous case of lag connection between wing and fuselage. In any case, these are just the first results that I wanted to share with you. We have now a complete overlook of critical crack lengths, of number of cycles, and of very high resistivity of this specific titanium alloy to human body. We still have to see combined effect of humid and salty chambers or environment, but titanium alloy is certainly excellent choice. And of course, all of us who are dealing with biomaterials know that nowadays this is a dominant alloy that we use in biomaterials, hip implants in particular. So I think I'm still on time. Well, 2 minutes late, but okay. Thank you.
Thank you, Alexander. Thank you very much. I hope we won't need these hip implants in the future, but anyway, you may ask some questions or comments or discuss this problem, please.
If we live long enough, everybody would need it.
So, Professor, thank you for your detailed and very interesting presentation. I would like to ask maybe in general, the question is to those 2 presentations. Did you consider other numerical techniques for crack propagation modeling, such as, I don't know, virtual crack closure technique, or just XFEM?
Not just XFEM. I mentioned that we also consider and use classical FEM because recently ANSYS provided this option by introducing this so-called SMART. I can't recall what is the acronym for. The last T is for technique, I know that, but SMART means that automatically mesh is following crack growth. So software itself allows you to use FEM and not to be forced to use XFEM. You know, evolution of this was that before 90s, nobody really did something really appealing and good in this field because FEM, classical FEM, was not capable of following the crack path. And then Belichko and his co-workers, they introduced XFAM, which is a bit of analytical expressions built in software, and that was revolutionary. And for decade or two, it was almost exclusively used to numerically simulate fatigue crack growth. But then again, people finally found out, even using this modern data, big data handling, maybe even artificial intelligence. I don't know how it goes, but now we can use also classical FEM. But other than these two techniques, we are not using anything else.
Okay, thank you for your answer.
Thank you. More questions? Okay. Thank you very much. Thank you, Alexander.
Thank you, Andrei. That was a real pleasure.
And this session is over. It's closed. Now we have coffee break, please. Thank you.
Sure.